Theorem: limit of sine x over x when x approaches 0 equals 1. Here is the first variation of this theorem, is the limit of the reciprocal. Because the reciprocal of 1 is 1, then the limit of the reciprocal of sine x over x, which is actually x over sine x, is also 1. Let's see another variation. Assume that k is a non-zero constant. Then, let's try to figure out what is the limit of sine of kx over kx when x approaches 0. I say that I can replace x by kx at the limit, because the limit of kx when x approaches 0 equals to k times limit of x when x approaches 0, which is k times 0, which is 0. Let's replace x by kx under the limit, and we get that. But now look at the theorem. Because kx approaches 0, then we can get easily that this limit is 1. But if kx approaches 0 and k is a constant, it's clear that actually x approaches 0, and we get another variation of the theorem. Limit of sine of kx over kx when x approaches 0 equals 1. But now we can get the other variation of this theorem. For any constant k, which is non-zero, we also get the limit of the reciprocal of the previous one, which is kx over sine of kx, also is 1. So here is the theorem and its variations. Again, because the limit is 1, the limit of the reciprocal equals exactly as the limit of sine x over x. And then we have the small variation of replacing x by k times x when k is a constant, and then the reciprocal of that. Example: limit of sine 5x over x when x approaches 0. The 5x is locked in the sine. We cannot distribute the 5x from the sine, but we can manipulate the x. If we have 5 here, then we know that this limit is going to be 1. But it's impossible to just divide by 5. I also have to multiply by 5. Now I notice that we have sine of kx over kx when k equals 5. And that's why I'm getting that this is the limit of 5 times sine of 5x over 5x. But using the constant rule for limits, this is just 5 times the limit of sine of 5x over 5x when x approaches 0. Using one of the variations of the main theorem, we know that the limit is 1, and then we have to multiply by 5 and we get 5. Another way, which is very useful for more complicated limits of this kind. What I'm going to do is I'm not going to write nothing below the sine of 5x and nothing above the x. Now I'm going to fill in. I want to complete to get the use of the limit. Here I must have the same thing as in the parentheses that go with the sign, so it is 5x. But if I divide by 5x, I also have to multiply by 5x. I put the 5x over the x because I see cancellation. Now I get that the limit now is actually the product of the two limits here. The limit of the first one is 1, and the second one is 5 by cancellation. And we get 5 as before. Be careful. Sine of k times x is not k times sine of x. If you make this mistake, you may get the right answer, but it is not acceptable. In mathematics, any right answer obtained by applying wrong rules is considered wrong. Example. Let's now take the limit of sine of 4x over sine of 7x when x approaches 0. Now I'm going to use this technique. Write nothing below the sine of 4x and nothing above the sine of 7x and leave some extra space on the fraction line. Now I'm going to fill in. If I would like to use the theorem, then sine 4x goes with 4x. But I cannot just divide by 4x, I also have to multiply by 4x. In order to use the theorem, I must have 7x above the sine of 7x. It means that now I have to divide by 7x. Now I'm going to split this to 3 limits. We know that the limit of the first ones is 1. And we get that. Example, limit of tangent 9x over tangent 3x when x approaches 0. First, I'm writing like this. Now I know that I have to multiply by the reciprocal of tangent 3x. The reciprocal of tangent 3x, which is also sine of 3x over cosine 3x, is cosine 3x over sine of 3x. Now I want to take those to the side because I know that cosine of 0 is 1. So cosine of 3x over cosine of 9x is just 1 when I will take the limit of x approaches 0. Now I need to focus on the second limit, and I'm going to do as usual. Under the 9x, I have to have 9x, so I have also to multiply by 9x. Above sine 3x, I should have 3x, which means that I also have to divide by 3x. And we are going to get 3 limits here. Cancel out. And as usual, the first two are just 1. And the third one is 9 over 3, which is 3. Example, limit of 1 minus cosine x over x to the power of 2 when x approaches 0. We need a small trick here. You have to pay attention to two important things. First of all, we have something over x to the power of 2. And second, the limit is x approaches 0. If we want somehow to cancel out the x to the power of 2 at the denominator, which is a 0 at the denominator, we really like to have something that has to do with sine of x, because sine of x over x in this limit, when x approaches 0, is going to be 1. You can view this as cancelling something over x when x is 0. So the only hope really to cancel the x's is to create a sine function instead of the cosine. We can do that pretty easily if we multiply everything by the conjugate of 1 minus cosine x, which is 1 plus cosine x. We get that. Here we have 1 minus cosine to the power of 2x, which is sine to the power of 2x. Now we can see that those two will be really easy to evaluate, and also I see that I don't care about the 1 plus cosine x because this one is not 0 when x is 0. I'm just splitting up sine to the power of 2x over x to the power of 2 to sine x over x times sine x over x. Here's the product of the three limits. We know that the two first ones are 1 and the last one is by substitution 1 over 2 because it is 1 over 1 plus cosine 0 and cosine of 0 is 1. Another way, it's starting from the second row is, first of all, get rid of the 1 plus cosine 0, which we know it's 2, and we get half time this limit, but this limit of sine to the power of 2x over x to the power of 2 is just the limit of sine x over x to the power of 2. And using rule of limits, we know that we can actually take the limit inside the x to the power of 2. And we get that.